A transformation, you can hear voices. Function as
poetry.
Should write a poem about that. All right, so got rid of those voices in our heads, and now we're off to learning about transformations. So a transformation takes something into something, and it takes, well, a transformation in general takes something and then massages it and makes it into something else. Okay, so it depends on what type of transformation we're talking about. We could take like I said last time, we could take a function and make it into another function. We could take a number and make it into another number. We could take a vector and make it into another vector. In fact, we could take a function and make it into a number, or we could take a vector and make it into a function, and we could do lots of different things. But for the sake of this class, a transformation or a function or a mapping will take a vector from one space into another space. Now those two spaces don't have to be the same dimension. It could be different dimensions, but it's still going to describe, as long as we have a well-defined function that, you know, the function has an input and then gives you a unique output. As long as our output's unique, then that's going to be a function. So in terms of these types of functions going from Rn to Rm, let's take, for example, this function that takes, let's call this, what should we call this? M, no. I'm trying to get creative, but I can't. So let's just call it T1. So T1, let's say, takes a function, or takes a vector from R2 and gives you, I was going to say a vector in R1, but what is a vector in R1? A point, or a scalar is what I was trying to get at, a number. And what I could do is I can define it a certain way where I take any random vector x, y, and then I need to do something with that x, y to get it into a scalar somehow. So maybe if I square the first one and then square the second one and then take the square root of that, so this will give me a scalar. Anybody know what this is called? It's just the magnitude, right? So we've seen that before. You can also think about this particular function as, if you've taken Calc 3, as a function of several variables that gives you an output of a scalar. Okay? So that's one type of function. So a little bit more interesting, let's say we take a vector in R2 and let's send that to a vector in R3. And so that means if I have an x and y vector in R2, my output needs to be something in R3. So what if I say x, y, and 0? This is a boring one. For those people that are good with visualizing things, this takes a point in 2 dimensions and brings it to what? Into 3 dimensions. It's still on the xy plane, right? So that's not very exciting. But it's still a function. It's a function going from Rn to Rm with m and n, or m and n being different. So if we have something a little bit more interesting, let's call this T3. let's go from R3 to R2. So this time I need to start off with a three-dimensional vector, so let's call it x, y, z. Or I suppose you can call it x1, y1, or x1, x2, x3, or something like that. But let's just call it x, y, z. And maybe this one goes, I need a 2D vector here as an output, so maybe x plus y and y plus z or something like that. And this is something that's not so regular now. It's a little bit more unusual, and I don't know if I can visualize this off the top of my head, but there's some geometry, I'm sure, that's going on with this. So it takes a vector in three-dimensional space and somehow puts it down as a vector in two-dimensional space. It's kind of like a projection, but I didn't make it a projection. It's a projection that's being skewed somehow because of the y's are involved in a couple of places. So I think it's a little bit more complicated than a projection. But anyways, these are some examples of transformations. Let's do some transformations. It just goes from R2 to R2. Examples. Those are usually nice and easy to visualize. What if I have a transformation that looks like this, that looks like that takes a vector xy and then it transforms it into, I think it's negative y x. Or it takes a vector xy and transforms it to x0. That one's a projection. Or we can, just any sort of combination. Any sort of combination, as long as we're starting in 2 dimensions, we're ending in 2 dimensions, these are examples of linear transformations. Okay? Questions?
The last one's not linear.
Oh, yeah. Yeah, this is just transformations. I didn't mean to say linear yet. We're going to define linear transformations, and we'll show that the last one is not linear. The others are linear, right, Hal?
Step number 1.
This one? Yeah. Okay. So our focus in this particular section is to study linear transformations, and we'll see that number 1 and number 6 are not linear transformations, but everything else is. And we'll see what a linear transformation looks like, and we'll define what it satisfies, and we'll define it and see what conditions it satisfies, and we'll mess around with them a little bit. Okay. So here's a definition of a linear transformation. It's the definition comes with 2 conditions that it has to satisfy, but these 2 conditions actually can be kind of rolled up into one condition that is basically the linear combination of these vectors or these transformations. So the first one, it says a transformation is closed under addition. So if we take a transformation of a sum of 2 vectors, it is the same thing as taking a transformation of those 2 vectors individually and then adding them in the new space. So this addition over here happens in the first space of the vectors, and this addition over here happens in the second space of the vectors, the resulting space. And then same thing with a scalar multiplication. If we take a vector and multiply it by a scalar before the transformation, it's the same as that if we take the transformation and then scale it in that new space. So with this addition and scalar multiplication combination, we could take a look at it. A linear transformation would satisfy this one statement, which kind of rolls both of those statements up into one. Okay? How's that so far? Is that cool? No. This is, will we? Maybe. Yeah. Yeah, with vectors, we'll see that it's if we can get a visual of this, then we can restrict our transformations into just a handful of visual things. I don't know if that even makes sense. Whatever. Let's see. Let's take a look at T2 here, or T3. T3 looks like it's a little bit more interesting. So let's show that T3 is a linear transformation. So T3 takes a vector in, what is it? From R3 to R2. So it takes a vector in R3 and sends it to R2. And the vector in R3 can be generically X, Y, Z. And then it sends it to X plus Y and Y plus Z. So, yeah, Jamie was saying this is a little tedious, but we'll run through it. We'll let A and B, or alpha and beta, A and B, be scalars, and we'll get two vectors, U. We'll let U equal to X1, Y1, Z1, and we'll let V equal to X2, Y2, Z2. And then we'll run it through this machine to see if we're going to get exactly what they have here. Let's see how we're going to run it through the machine. So we want A, U plus B, V, where A and B are scalars. And so we'll scale each one. So this is going to be A, X1, A, Y1, A, Z1. And then we're going to add that to the vector B, X1, B, X, Y, X2, sorry, Y2, and B, Z2. So when we add that, we get this big vector that looks like this. All right? And so we want to take the transformation of this. What is this going to be? Now, at this point, we have to pretend that this whole thing here is your X, and this whole thing here is your Y, and this whole thing here is your Z. So this is your X, your Y, and your Z. And according to our output, this is supposed to be X plus Y. So I'm going to take X, which is A X1 plus B X2, add that to Y, which is supposed to be A Y1 plus B Y2. All together, so this is going to be one scalar here. And then I'll take Y, which is A Y1 plus B Y2, add that to Z, which is A Z1 plus B Z2. And if we take this and do some appropriate factoring and things like that, hopefully we would get what we're supposed to get. So what I'll do is I'll break this up into this, and then the A's and the X's, A's and the Y's together, and then the B's together. So this is going to be AX1 plus AY1 plus BX2 plus BY2. I should have done one with the zeros. And I'll do the same thing. AY1 plus AZ1 plus BY2 plus BZ2. So what I'll do at this point is I'll look at that. That's a vector in R2. Now in R2, if I have a vector in R2 that looks like this, it looks like I'm adding the components. It's the same thing as adding those vectors. So I'm just going to cheat a little bit here and save myself writing another step. And I'll break this up to two separate vectors. And breaking this up to two separate vectors, I see that this first vector has an A out as a scalar multiple, so I'll take the A out of the first component, and the second component that comes out is one A outside of that vector. And after I take an A out of the first component, I have X1 plus Y1 and Y1 plus Z1. And then this plus over here with another same deal with a vector, take that out, X2 plus Y2, Y2 plus Z2. And well, that's X1 plus Y1, Y1 plus Z1. That's the same thing as a transformation of X1, Y1, Z1. And so I'll take my A out here. I'll take this vector, which is really the transformation of X1, Y1, Z1. And the same business for the B. This is another transformation, but this time it's X2, Y2, Z2. And I'll notice that that's just U and V. So I start off with a T, the transformation of AU plus BV, and then I end up with A times the transformation of U, B times the transformation of V. So that shows this statement, and that proves that this transformation is linear. Separately? Probably. We're kind of doing this constant multiple twice here by doing it this way. So yeah, probably. Because I realize that this something X1 plus Y1 and Y1 plus Z1, that's pretty much that transformation, except instead of just a vector X, Y, Z, it's X1, Y1, Z1. Okay? So usually for things like this, it's appropriate to show if something is linear, but it's also good to show when there's something that's not linear. So let's take one of our things where Hal said it wasn't linear, like this last one. That's supposed to be not linear, and let's show that it in fact is not linear. So let's take a shot of that. And let's pass it through that test to see Well, let's do it one by one. Becca said it was easier to do it one by one, so let's see if we could do it one by one. It has to be closed under addition. So if we add two vectors, let u equal x1 and y1, and v equal to x2 and y2. And let's add those two vectors. So T6 of u plus v is the transformation of u plus v. So x1 plus x2, y1 plus y2. Okay? So here we're just testing the first one. We're not doing this combo business. We're just testing the first one, the addition. So according to the transformation, our result should be, remember that this is x and this is y. This is x and this is y, according to our transformation definition. So our x is x1 plus x2. Our y is y1 plus y2, and then we have to add 4 to that. And our new y output is 7 plus y, which is y1 plus y2. Now the thing about this transformation is, regardless of how you split this up and break it up and things like that, I can have this to equal to, if I switch the order around the addition, x1 plus y1 plus 4 plus x2 plus y2. And then I have 7 plus y1 plus y2. It looks like if I just collect this stuff, I have x plus y plus 4, 7 plus y. So that looks like it's t of x1, y1, which is u. But unfortunately, this is not the t of x2, y2, because it looks like I might be missing a 4 here. I need another 4 here, and I need a 7 down for the second one for this to be a transformation of the T6 transformation. So in this case, we don't have so this didn't work for us. We're not able to split this up into T6 of u plus T6 of v, which is what this is supposed to equal to if it was in fact linear. So because we have to stop here, we have to say that this is not linear. Okay. All right. Questions? Linear, not linear? Proving something is linear. All right. So now that we know what a linear transformation is and what it does do, we can take a look at what a linear transformation really should look like. So if we're talking about a linear transformation from one vector to another vector in whatever space you're dealing with, these linear transformations should be able to be rewritten as a matrix. So an m by n matrix, well, this first one says that an m by n matrix is a linear transformation. So what it does really, is that it takes a vector and it does something to the vector. And the thing that it does to a vector the way it transforms it is that it transforms it linearly. And so if this is supposed to be a linear transformation, then it has to satisfy the scalar addition, or the addition and scalar multiplication. So we haven't proven anything in a long time, and I think this might be easy enough to prove. So let's see if we can prove it. So for this to be true, we have to be able to take two vectors, u and v, and somehow make it to tu and tv. And just to get ourselves warmed up, these vectors u and v are in what space? Rn or Rm? It should be in the domain space, which is Rn. So this should be in Rn. Okay? Now, according to the definition of this type of transformation, this type of transformation should be able to be rewritten as a matrix multiplication where we have matrix A applied to the sum of these two vectors u and v. So, no, let's not talk about the columns of A, but the vectors themselves are outside of A, and they're the ones that are going to get transformed. Yeah, so this is a matrix multiplication, and these vectors, we can take a look at these vectors as column matrices. Yes. Yes. So n is the domain space because that's where it starts. Well, it turns out that this is one of the properties from matrices, so this actually distributes. And because it does distribute, that's the definition again of T. And so we can say T A of U plus T A of V. I guess I should put parentheses around this. I tend to drop the parentheses because the transformation and the matrix are really the same thing. And so with matrices, we don't usually put parentheses around. So I kind of look at this, quote, transformation as a matrix anyways. So this satisfies the first condition. The second condition, if we take a vector u and then we multiply it by a constant c, a scalar c, it should also work out. Again, we're going to do this transformation and change it into a matrix and language matrix, or matrix of languages, or matrix, the language of matrices. And and it's another property where if you have a matrix times another vector or a column matrix that's being multiplied by a constant, you could take that constant out in front. And so this is just the constant, or the scalar, times TA of u. So the second condition is satisfied, so we're done here. So all these matrices that we've been looking at and been studying and doing stuff with turns out to be linear transformations. Yeah.
So in this case, you just replace the, I guess, wording for the transformation with, I guess, the symbol for a transformation with the symbol for a matrix.
Because that's how it's defined here. The part that is probably easy overlooked is this step where we can do this, and these are from the properties of matrices. Well, what we've shown here is that a matrix is really a transformation. Not only that, but the matrix is actually a linear transformation. Yeah, so the parentheses on this side?
Oh, yeah.
Yeah, so you're plugging something into T. This parentheses is a multiplication, of a matrix with a vector, and then that splits up. All right. Well, let's see what that means. Let's make up a matrix. It's always dangerous, right? Well, I was going to say the identity matrix, but let's not waste our time with that because that identity matrix isn't going to change anything. So let's make up another one that would change something. Let's see if I could do this. Maybe Hal can do it for me. I'm looking at this one, Hal. Can you help me out? This one, the one that we proved that was an actual linear transformation, x plus y and y plus z. Well, no, I want to know what the matrix is. Jamie, you too? 3 by 2. 3 by 2. 1. Yeah, it's 2 by 3, right? So 1, 1, 0, 0, 1, 1. Okay. Whew. All right, so this is a matrix. And this matrix is supposed to be a linear transformation, right? So if it's a linear transformation, then it should take matrices. So let's see what this matrix actually looks like. So let's call this example A. What was A3. So A3 is a 2 by 3 matrix. Okay? And just by looking at this, if I want to apply A3 to a vector, what size does my vector have to be? Well, I want either, I want one column. So 3 by 1. So this has to be a 3 by 1 matrix, right? So if I apply it to a generic x, y, z vector, a 3 by 1 vector, what am I going to get? Well, in my first component, well, first of all, my output is going to be a what by what matrix. So what by what? This is a 2 by 3 and a 3 by 1. So this is going to be a 2 by 1. And so how's that going to look like? It's going to be x plus y plus 0. Are you seeing it? It'll be a 0 times x is 0. We have y plus z. And then we say, whoa, that's like the transformation that we saw earlier. This is like the transformation that we saw earlier. Same reaction. What? And then there's a new reaction. Okay, so it turns out that a matrix can be written in a function form, if we want to call it that, where it's a transformation. And then in this particular case, we happen to have gotten lucky. Well, I thought about it really hard. But we happen to have gotten lucky, I'd like to think that we actually were able to represent that same transformation with a matrix. So what we're saying here is that our original transformation from the other page, where we took a transformation from R3 and brought it to R2, via this transformation or this function is the same thing as this matrix that we just made up. And so this is an example of how a transformation and matrix can work together, or how they're the same thing. So mathematically, we can express this. If you have a computer algebraic system that computes, that can deal with, abstract objects like functions, then this is nice and easy to deal with. But if you have just a computational system where all you're doing is computing matrices with something, then maybe a matrix form will be more handier. More candy. I mean, have you heard of buyback candy programs? Where if you collect all this candy and then you're not going to let your kids eat it all, you donate it or send it to somebody else. Yeah. All right, let's move on. All right. I think I wanted to do a little tangent diversion and talk about linear transformations and how that would look like graphically. That's what I keep saying. It's only a suggestion, right? Okay. So let's say my left space is the domain and my right space is my range. And I'm just going to go from R2 to R2 here. Just keep it simple because I can't go to R3. So I have this matrix over here will represent a transformation that I have. And in this case, I have, I should have done a two-dimensional example. I have the identity matrix, which is going to take a vector and send it back to another vector, which is the same vector. So that's not very exciting. But if I change this matrix, let's change the matrix. Let me change by making this into a 1. What happens? Ooh. So this transformation matrix apparently does something to the output. It takes a vector. Well, it takes these dots and it kind of stretches it. What's this called? It's not shearing, is it? Is it shear? This is shear. Let's make this into a variable so that we can see how it changes. And this is going to go from -5 to 5. So the n over here, that's the upper right hand of that 2 by 2 matrix, is changing with respect to whatever this number is. That's how this number is changing. So right now it's negative, and the negative shearing kind of stretches this object over and brings it over to the other side, or positive and negative sides of x. So this is interesting. And because it's represented by a matrix, this is a linear transformation. Now, let's see. Let's change this back into 0, and let's change the second one and make that into that variable. Now look at how this is going to change. So with negative values, it kind of extends a certain way. Positive values, it extends another certain way. Well, let's take a look at this algebraically and see how this actually looks like. If we take a look at this vector or this matrix, what is it? 1 times n and 1 n 0 1, and then let's apply it to a vector x y. It's going to take your x vector and it's going to say x plus n times y and then 0 and y. So it looks like it fixes y. The y doesn't change, but the x changes. Okay? In fact, this might even be more complicated to look at. I mean, if you can visualize this, that's great. But if it's a little bit more difficult to visualize if we're dealing with x and y arbitrarily. So why don't we simplify it and take a look at nice vectors, lines or vectors. If we're we're looking at vectors after all, right? So let's take this 1 and 0 1. And let's apply it to the vector 1 0. This becomes 1 and 0. That didn't change much, huh? All right, let's take the matrix now, our transformation matrix, and let's apply it to 0 1. And this becomes, what's this become? N and 1, is that right? Okay, how's this interesting? Yeah, so it depends on what n is equal to, right? So if we were to do this by hand without the use of computer technology, what we're saying here is that we're saying that this vector 0 1 gets mapped into another vector and doesn't change it. But if we take a vector, I'm sorry, the first vector was 1 0. The next vector was 0 1, and that is going to become, your x is going to change. So let's say, I suppose if we don't have a thing, we should say n is equal to 5 or whatever. Depending on whether n is positive or negative, your y value is still going to be 1. But your x value has now changed. So your vectors, depending on what n is equal to, would be those things, right? And so if we go back to the animation here, and let's change it back to the thing that we were looking at. If you see, the x's don't change. The one where the y, the blue and the red dots, if you just focus on the blue dot, really. Actually, which blue dot? You know what? I think maybe we should put a vector. So the vector is 0 0 0 1. Can't see that vector, huh? Just get rid of all these other ones for now. I guess we can leave the dots because the dots are cool. So this is the vector that we're looking at right here, right? And if we try to follow that along, that vector just kind of moves. It has the y value of that vector doesn't change, while the x value changes according to whatever that number is in the upper right-hand corner of our matrix. So there it goes. This is a shear. Okay. So that's one. I guess you can call it a family transformation, depending on what n is equal to. Let's see another interesting sort of transformation. And the interesting transformation is it's interesting because it's, well, I don't know. It's just interesting. Let's take a look at another matrix. What should this matrix be? 0, -1, 1, 0. What do you think this does? Let's see. Let's apply it to, let's call this A, so I don't have to keep rewriting it. Let's apply A to 1, 0 and see what happens to this. What happens when you apply it to 1, 0? 0, 1. And let's apply 0, 1 to it. I'm applying the vector to the matrix. So 0 times 0, -1 times 1 is -1. 0 times 1 and 0 times 1 is 0. I guess it could be. And so if we do this in general, A applied to x, the vector x, we can imagine 0, -1, 1, 0 applied to xy. Negative y and x. Hey, that was one of my other transformations, wasn't it? All right, so let's, can you, just by looking at the x and y, outputting to negative y and x, can you see how this thing looks like? Let's take a look. Perpendicular to the original one. 0, -1, 1, 0. Looks the same. Wait. The colors change. Perpendicular? Oh, there's, oh. Is it perpendicular? So was there, what do you guys think? Did something happen? Was there a reflection, a rotation? Which one is it, a reflection or a rotation? Clockwise? Is that clockwise? Look at the clock. Right, that's how you can tell if clockwise or counterclockwise, right? That's, I always look at the clock. I always look at my wrist. Then I could tell. So in this case, I think our arrows went from going up to pointing to the left. So I think that is going counterclockwise. Did the dots follow the same thing? So this dot was here, and now it's here. The red dot. So if you're colorblind, sorry. This is
So did it go the whole way around to the right, or did it go a little bit to the left?
did it go?
Because I don't see how we kept it going.
Yeah, I don't see.
170 degrees minus.
Yeah, like, couldn't you just say either?
Did you say either? Well, it went 90 degrees clockwise. Okay, so counterclockwise. Justin.
I was looking at the right one first.
Yeah.
And then looking at the
So
left.
kind of like right hand rule.
Exactly.
Yeah, it's like,
It always has a vector.
No. 2 pi, 6.28. All right, let's take a look at this. So, I changed my matrix to cosine n, negative sine n. So when n is equal to 0, I have cosine of 0, which is 1, sine of 0, which is 0, sine of 0, which is 0, and cosine of 0, which is 1. So this is the identity matrix when n is equal to 0. Now, if I change as my n here is now 0, I'm going to let my n go from 0 to 2 pi. Let's see what happens. Or pi. What's pi over 2? Pi over 2, yeah, but what's, yeah, what's pi over 2? 1.57-ish, right? In radians. So we're doing things in radians. When this number gets to about 1.572, I'll stop it. Say when? Whammy, whammy. Oh. I guess, but it was more exciting that way. So this is 1.57, which is our result from before. And cosine of pi over 2 is 0, sine of pi over 2 is 1, so this is negative 1. Sine of pi over 2 is 1, and cosine of pi over 2 is 0. So this is the rotation matrix. Now this cosine sine business is called the rotation matrix, where you're able to rotate whatever it is whatever you're doing in 2D. Yeah. It has to be in the specific order. If you change the negative somewhere, if you change the sine and cosine, it might be going. What? Yeah, if you rotate the matrix, it might go counterclockwise or clockwise.
what if you want to rotate something that's, you want to do it just like certain?
So if you want to rotate it in 3 dimensions, then then you'd be dealing with a 3 by 3 matrix because you're going from R3 to R3, and then the robotics section at the end of this section would be some interesting reading for you.
So transformation from R3 to R3 or from R2 to R2.
R3 to R3.
Not also from R2 to R2, would just be a movement.
Oh yeah. So all these things are movements of some sort.
Transformations in the same dimension.
Yeah,
What
but
if you go from R3 to R2?
then they can still yeah, so they can still go, you can still do that, yes. There are linear transformations. And linear transformations are defined from any space to any space. So you can go from R2 to R5, and then,
Right,
you can see
just
some
trying
movement there. Yeah,
Visualize
Anything.
the implications.
yep. So this is a nice way to get to see these matrices and how these matrices work as a transformation. So we saw the shearing matrix that kind of takes the vectors and stretches it in different ways, and then we have this rotation matrix now. Formally, I think it's called a rigid rotation because you're rotating it without changing or stretching or anything like that. So yeah, so that's cool. All right, so a few things in that little side tangent that I just took, we kind of didn't really establish, but we can try to generalize it to some of these other ideas. So the first idea was the idea of instead of having a generic x, y vector, we could take a look at a set of basis vectors for that particular space and see what the transformation does to the basis vector, since dealing with basis vectors seems a little easier. So if we have a linear transformation and T is a matrix transformation, I don't know why they didn't call it A. I guess this should have been A. Then you have what you could do is you can define your matrix by what your transformation does to each of those elements. What? What? So, let's take a look at this transformation that we saw earlier. This transformation that we saw earlier. T4. If we take this transformation that we saw earlier and try to figure out what happens to our basis vectors, which is in 2 dimensions, it's just 0, 1, and 1, 0, or 1, 0, and 0, 1. So if we let our first basis vector to be 1, 0, so T4 applied to 1, 0, tells us this is going to be, your x is going to go down in the bottom and your y is going to be negative up on top, which is still 0. And then 0, 1 would look like x is now 0 and y becomes negative y, becomes that. So what this theorem is saying is that we can take these output vectors where we put in our basis vectors, and your corresponding matrix here, A, should be equal to 0, 1, negative 1, 0 as columns of that vector. And this is, in fact, what we saw on the previous page, how that transformation works. Yeah?
So up there when it says A equals T to the 1, it goes to T to the 1 here?
Oh, maybe that should be M or N? N. Good catch. So these are columns. Of your matrix A, and there are n of them. Same dimension as so the domain space is the starting. No, columns.
But those are R2.
Well, in this case, it's 2 by 2, so we're going from R2 to R2. So it'd be more interesting if we're going to from R3 to R2, in which case this is still going to count the number of your whatever dimension your domain is. Okay? So if we have a well-defined transformation, then we should be able to find our matrix. Or let me rephrase that. If we have a well-defined linear transformation, we should be able to define our matrix by applying it to our basis vectors. Now, this is our standard basis vectors, but if we apply it to another set of basis, then it'll still work, but it'll look different. Ooh. Yeah, let's not talk about that right now. Applying just means one way to, quote, apply is to, you know, when you have f of x equals x squared, what we're saying is that f of 2 is 2 squared. That's how you apply. Now, if it's more than two things that you have here, you just take whatever the first number is, and it goes, according to this definition of this function, it goes down as a second component. This goes as the first component with a negative, and that's how you apply. That's how you apply the transformation. To apply the matrix, applying the matrix is like taking the matrix, and when you say applying it to a vector, it's the same thing as making your vector into a something by one matrix and doing a matrix multiplication. So the word apply here can mean matrix multiplication, or can mean putting the vector into the function or the transformation, just like what we used to do in calculus. Okay? And so we have a handful of vectors. We saw a couple of vectors, the shearing and then the rotation, but then there's other vectors that, or other other transformations that they like to talk about. So here are three of them. The first one we already talked about with the visual example and graphing calculator program. The rotation matrix. It's a counterclockwise rotation by measure of theta. They talked about this projection onto a line and a reflection about a line. So here are a couple of other interesting things we talked about. We also talked about shearing matrices. I think it's 1, N, 0, 1, and 1, 0, N, 1. For different values of N, it's going to move your vectors. It'll drag your vectors along the X or along the Y. Or, I mean, if we have different values, N and N, for those wings, then we can imagine stretching it along the X one way and stretching it along the Y a different way. So this projection onto a line was discussed in the book, in the main part of the book. This reflection about a line was discussed in the problems. So it might be good to take a look at where those things were defined. And let's see if we can reflect this about a line. What would be a good line to reflect on? Y equals X is kind of boring. Let's put something different. What? So a reflection about a line means you have a line, and whatever you have on this side will get reflected onto the other side. And that line is defined by a vector, D1 and D2. So if we let D1 equal to 1 and D2 equal to 1, then that would just be the y is equal to x line. So you want to try a reflection about y equals to x line? That's kind of boring, but I think it'll be, well, all right, so what should we do? So the line has to be a vector coming from, let's just do 1, 1. So a reflection about 1, 1 will give us, this is 1 half on the outside, so we need to throw 1 half on the outside. And the inside, if D1 and D2 are both equal to 1, this is 1 minus 1, that's 0. This is 2. This is also 2, and this is 0. So it kind of looks like the rotation, but is it a rotation? It's not supposed to be, right? Did it actually rotate? Okay, so what might be helpful if we draw y is equal to x line and see that that's the reflection line, and the arrow that was once pointing up here got reflected into pointing to the right. The red dot and the green dot switched, and the blue dot stayed the same. Okay? All right, so those are some basic transformations in R2. There are transformations that exist in many other dimensions. So the fact is that if it's a linear transformation, we can write it as a matrix. And if it's a matrix, then it is, in fact, a linear transformation. All right, that's it.